Oh, hi. In the last lecture, we talked about the equivalent circuit of induction machines, and today we will give more detailed information about how can we express power and torque in induction machines using that equivalent circuit. So just to have a reminder, this is the equivalent circuit, and this is to show the primary side or the stator side separately. So it is really similar to the equivalent circuit of a transformer. So we have R1 and JX1, we have the core losses and the magnetizing reactance. Then we have like different E1 and E2 magnitudes because of the frequencies changing. It's different from a transformer. And we have R2 over S and JX2. Actually, what we did is we can just refer those circuits to the primary side, and at the end we can express everything with respect to the parameters measured from the primary side or the stator side. At the end of the day, it's not really easy to measure the real rotor currents. What we measure is the referred rotor currents with respect to primary or rotor side. So again, you can watch the last video about what those components are meaning. But today we will talk about the power flow. Okay, so first we have, here we have the total input power coming in. Okay, input power. Then I'm dissipating some of it in the copper losses, stator copper losses, let me say. And there's also core losses, stator core losses. And then I can express the remaining power like that. So let's define those things. First, I have the input power. It is V1 phase voltage times phase current times the power factor multiplied by 3. Don't forget all that equivalent circuit that we are discussing is per phase equivalent circuit, but it's per phase power or per phase torque is rarely or never used. So don't forget to multiply those things by 3. So 3V1 I1 cos theta is our total power. Then I have the stator copper losses. So these are the dissipative heat in the stator windings. So again, it is I1 square times R1. So again multiplied by 3. So this is converted to heat in the copper winding. Then I have the core losses. So core losses technically is equal to that voltage. If you just go back, if this is E1, this is E1 square divided by RC is the power dissipated here. But since that components are small and the voltage drop here can be ignored, what we can do is we can move that parallel branch to the primary terminals. Okay, so then instead of E1 squared divided by RC, I can represent it as like almost equal to 3V1 square divided by RC. And this is the core losses. This is the heat generated in the electrical steel laminations of the stator. So if I subtract, and again don't forget, if you have inductive components, there's no real power dissipation in those inductive components, so I can subtract these powers. Okay, so I can subtract the copper losses and the core losses from the input power. Then I can find the electric power transferred to the rotor side. So we call it the air gap power. So that is the total power that flows through the air gap between the stator and the rotor. Okay, or you can represent it like that. So let me go back. So again, all that air gap power, and again, if you think about it, there will be no power dissipation, real power dissipation on that component. So air gap should be equal to I2 square times R2 prime over S times 3. So this is air gap power per phase in the power I have shown here. Anyway, so you can represent it like that. So this is the referred power that is going to the rotor side, and this is R2 prime over S. But then this power shouldn't be dissipated all to heat, right? If it is just dissipated all to the heat, then what happens to the mechanical power? At the end of the day, this is a electrical machine, electrical motor, so we don't want to operate as an electric heater if we just convert all the input power to heat in the rotor. So actually we can divide, and actually there's also the derivation of those equations in your textbook. I'm skipping those parts. So the equivalent circuit R2 prime over S is, you know, just a conversion that we represent to increase the input voltage because the frequency is changing in the rotor side. So then we multiply those things by slips, or divide by slip to get equivalent E1 and E2 parameters. But at the end of the day, the real power dissipated in the rotor resistance, there's some real resistance there as well, it doesn't change. It's okay if this is some joules, some watts, it has to stay same. So actually that copper losses should be in the form of 3 I2 prime square times R2, right? R2 prime. So then if this is, let me write here, like rotor copper losses, right? So then, and I know air gap power, P air gap is equal to 3 I2 square, okay, times R2 prime over S, when it is the total power dissipated here. So if 3 I2 square times R2 prime is the heat converted to heat, what about the other component? Oh, sorry. So what I can do is I can subtract, okay, if I subtract P air gap minus P copper 2, then that should be equal to the mechanical power, right? That is not converted to heat, but that is converted to mechanical energy. So let's do that. So 3 I2 prime square times R2 prime over S minus the real power dissipated in the stator resistance, okay, times R2 prime. Okay, so if you do that, this is a component of 3 I2 prime square. Okay, these are common components. R2 over S minus R2 is equal to R2 prime 1 minus S over S. Okay, so again, that is, okay, that is the mechanical power. Right? And that component, I mean, that is how we represent it like that. Is that component 1 minus S over S. We will use that relation quite a lot. This is not a real resistance, but a component to represent the mechanical power. Okay, so that means, I mean, we did similar things. For example, in core losses, that a resistance, it is not a real resistance that you can measure with your multimeter, but that is a component to represent the core losses. Okay, or in synchronous machines, okay, we show it like there's a EF or something like that, but EF is not actually a AC voltage source, but it is the link between the electrical system and the mechanical system. And here that resistance 1 minus S over S R2 prime is not a real resistance. It's not dissipating heat like in the form of electrical heat, but it is a component which has equal power dissipation that is equal to mechanical energy converted. So the real power, the real heat is still generated in the rotor copper losses I2 prime square times R2 prime, but the rest of air gap power, because you are transferring some power from the stator, and only that part is converted to heat, but the rest is converted to mechanical energy. So actually, if you put those things on, so we have the air gap power coming in, and we have the, again, 3, let me write it here, I2 prime square times R2 prime is the rotor copper. I mean, it doesn't have to be copper. I think it can be aluminum as well, but we still call it copper losses, whatever. Then that component 3 I2 prime square times R2 prime 1 minus S over S, and that is the power converted to mechanical energy. And if you add these two resistances R2 prime, let me write it here again, R2 prime plus, okay, 1 minus S over S times R2 prime, that is equal to R2 prime S cancels out, sorry, R2 prime over S, and S cancels out, so it is R2 prime over S. So that is how we divide these two components into two. Again, in some books, instead of R2 you see RR, and again I'm using those things on purpose just to get you familiar with different representations. So just don't try to memorize it using the R2, RR or something, that kind of equations, but try to understand its meaning. It will be much easier. So again, we have air gap power, then some part of it is converted to heat, but some part is converted to mechanical energy. And let's have a look at that components, and let's try to check it, double check it. So let's have a look at what happens to those components if the slip is 1. So for example, slip is equal 1, rotor not rotating, right? So then R2 prime is still the rotor heating is constant, it is there, and since rotor is not rotating, there shouldn't be any mechanical energy. Let's do that, 1 minus S over S, and when you put S is equal to 1, so that resistance will be 0 when the rotor is not rotating, okay, when the rotor is not rotating. And again, so actually we did it for the last week, so for S is equal to 0, so rotor at synchronous speed, okay, then you will have R2 prime, yes, it is there, but R2 prime, 1 minus S over S, when you put slip is equal to 0, that is 1, slip is equal to 0, so that is equal to infinite. So this is like open circuit, so that means if this is open circuit, then that means there will be no current I2 prime or IR as shown here, so that means there will be no air gap power, so you cannot transfer any power to the rotor side at the synchronous speed. Okay, again, let's have a look at that component. If the slip is, let's say if the slip is 1, okay, so there's no mechanical power, then the slip is, let's say, 0.5, then it is 1 minus 0.5 divided by 0.5, it is 1 RR. Then let's say slip is equal to 0.1, so that means 1 minus 0.1, that is 0.9 here, divided by 0.1, so it makes 9 RR. So it will be at 0.1 slip, okay, that resistance, sorry, will be 9 times of the rotor copper loss. So at for example, again, it doesn't mean the total efficiency because we have the stator components. So for example, for slip is equal to 0.1, 10% of the air gap power will be transferred to heat, and 90% of the air gap power will be transferred to mechanical energy. Again, you know, including the stator losses, our efficiencies will be less than 90%, but you see how the efficiency changes with slip, and we will discuss those things in the next videos. Okay, so once you put everything here, then you have the equivalent circuit like that. And again, that parallel branch can be moved to the primary side or can be left here. So we have R1, JX1, RC, JXM, they are the same. And we have JX2, R2, again, you know, that should be like the referred values in our convention, but don't worry about that one. Then we have two series resistances. One of them is R2 prime, just for heating of the rotor windings, rotor bars, and the other one is converted to mechanical power. So we have the input power coming in, we have the air gap power, okay, here we have the P air gap flowing in, and then we lose some heat in the rotor windings, then that is the, you know, converted from electrical side to the mechanical side. Okay, so then you will see some different definitions. So first we have the gap, okay, air gap power 3 I2 prime squared R2 prime over S. Then we have the rotor copper loss, okay. So when by using these two, okay, by using that one and that one, you can see copper losses in the rotor winding can be represented as air gap power. So this is, you know, just multiplied by S. So this is slip times air gap. So that means once, for example, slip is 1, as we discussed just a few moments ago, if the slip is 1, all the power is converted to heat in the rotor windings. If the slip is 0.5, then half of the power is dissipated as heat, and only half of the air gap power is converted to mechanical energy. However, if slip is 0.1, then 90% of that power is converted to mechanical energy, and only 10% of the air gap power is dissipated as heat. So you see, you know, between air gap power and the mechanical power, the efficiency gets better as the slips get smaller. But again, this is like not the total induction machine's efficiency, because we have the stator components as well. Okay, then another definition that you can see is the gross mechanical power. Gross in Turkish means brute. Okay, so it is the power, okay, that is completely converted to mechanical energy. So you have the air gap power, then you subtract the rotor copper losses because it's an electrical loss, then the rest is gross mechanical power. But then that gross mechanical power isn't always equal to the useful mechanical energy for us. Why? Because we have, you know, friction and windage losses and so on. So that gross mechanical power, so we just step from electrical system to the mechanical system. So let's find that one. So again, gap power is that much, and mechanical power is the power dissipated in the 1 over s divided by sr2 prime component. And again, you can see, that part is the air gap, and sorry, that's that part. That's okay. So that is the air gap power, as you can see. So mechanical power, similar to the copper, instead of S times P air gap, it can be represented as 1 minus S times air gap. And again, once slip is 1, so you can see there will be no mechanical power. Okay. So then again, another interesting, we will discuss it in the previous weeks, but there will be some cases where slip can be negative or slip is larger than 1, and we will discuss those cases as well. Anyway, so gross mechanical power is the total power converted into mechanical form. But after that, for example, if you would like to use T net, remember, so T net is equal to J times d omega over dt. So in that net torque, okay, so we need to use net power, because not all the mechanical energy converted can be used to derive the mechanical load, but there may be some frictions and that kind of things between gross power and net power. And in some books they say the shaft power. Okay, shaft power is the net power. So net power is gross power, that we obtain from the equivalent circuit parameters, but what we don't represent in our equivalent circuit is the, for example, frictions in the bearings. Maybe there's a fan connected to the shaft of the motor. They also require some mechanical power. So you subtract those, rotational losses or any power dissipated as heat, but in the mechanical form inside the machine, and then you obtain the net power. So that net power should be used in mechanical system calculations. But from our electrical circuit representation, the power dissipated in that resistance shows us the gross mechanical power. Maybe it will be easier if you just go over through that figure. So here we have the input power. Remember, it is 3 V phase I phase times cos theta. Okay, so that is the total electrical power that we sent from our voltage source. Then we have the stator copper losses. Okay, so it is 3 I1 square times R1 or whatever. And then we have the iron loss, or they are like core losses, and it can be like if the parallel branch is moved to the primary side, 3V1 square divided by RC. Okay, core. Then after we subtract these two, then we get the air gap power. Okay, then in the air gap power, then we have also the windings in the rotor. Then we have the rotor copper loss. It can be represented as like 3 I2 prime square times R2 prime. Okay, then the rest, okay, then the rest, there's also straight load losses like eddy current generated and that kind of external effects, but you can ignore those things for this course. So for mechanical power, so this side is the gross mechanical power, and that is 3 okay I2 prime square. Okay, so I would like to go back. So I would like to find that power. That is our gross mechanical power. okay, times R2 prime times 1 minus S over S. So then, some of that load is, some of that power is dissipated as heat in the mechanical form. Mechanical losses, I don't know, bearing loss and other frictions, etc. Okay, then you subtract that mechanical load, then you have the actual shaft power, or it can be also called as like net power. So then from here you can have T net, and if there's a load connected to here, or let me write, this is the electromechanical force, maybe there's some mechanical load here as well, and you subtract that one, and if this is still larger than those things. Oops. So let me write it here. So this is your electrical minus, maybe there's some, maybe you are lifting some load, let's say it's a crane or something like that. So if your torque, okay, is larger than 0, depending on inertia of the system, then you will see if it accelerates or decelerates. Okay, but from here on, now you are in the mechanical domain. Actually, that part is also in the mechanical domain, and that one is not represented in our equivalent circuit. So the boundary of our equivalent circuit is here. Okay, so here is represented by the equivalent circuit. Okay, cool. So again, I'm not going to discuss about the numeric efficiency calculations. We will do that in the next videos. Of course, efficiency is output power divided by input power. So we divide those things, and again, the efficiency calculated from equivalent circuit can be different from real efficiency, because our equivalent circuit doesn't represent the mechanical losses, friction losses, so on. So in a normal calculation, efficiency calculations, of course you need to put those things in. And again, there is nothing like friction per phase, or mechanical losses per phase kind of representation. So once you get into the mechanical domain, don't forget to multiply your per phase losses or per phase power to total power by multiplying by 3. Okay, so again, there's an example, but I would like to solve it in the restation R. Okay, thank you.